I'm Xiaoju Wu. I'm from eBay. I'm a big data engineering at eBay now. Today, I'm going to share some of the details of our work on DPP, which is Dynamic Partition Pruning and Runtime Filter. Okay, today's agenda is, so firstly, I will introduce how, I think you should already know the Dynamic Partition Pruning in Spark SQL Engine Optimizer. And but the current implementation in Spark community version, we cannot support dynamic partition pruning in adaptive execution. So in eBay's Spark SQL engine, we optimize this part to support DPP in AE. This is the first improvement I want to introduce. And secondly, I'm going to introduce the equivalence inferring that we optimized for DPP. And the third part is runtime filter, which the semantic is a little bit similar with DPP. And I want to introduce how we implement runtime filter and some tips on runtime filter, for example, like when should we infer runtime filter, and how we support multiple columns join, and how we plan a runtime filter subquery, and how to keep the capability with DPP, and also introduce a little bit on the exchange reuse implementation, and at last, the performance results. So how we support DPP in AE? I think in AE that the subquery reuse logic, planning logic, and the exchange reuse logic is totally different, because in AE, we use the subquery map, which is generated in insert adaptive Spark plan. And for reuse exchange, we don't use the reuse exchange rule. We use the stage catch, which is in AE logic. So to support DPP in AE, firstly, we should extend the build subquery map in insert adaptive Spark plan rule. We need to put the DPP subquery into the subquery map. And then when we plan the adaptive subqueries, we reuse that subquery from the subquery map. And also the exchange reuse is happened, and the stage is replaced by stage catch in AE logic at runtime. So we need to put the DPP exchange reuse logic into the AE logic. But one thing to notice is that the stage reuse may fail in the runtime AE logic. We cannot know, just like the pre-calculated rules, when will the exchange be reused. So if the stage reuse fails, we need to fall back. So in this way, we import a new EXEC class, which is named Adaptive Subquery EXEC. This is similar with the Adaptive Spark Plan EXEC, which is to wrap the plan, and the plan may change at runtime. So this class is to wrap the DPP subquery, and the subquery on this node will change dynamically and even fall back to true. So by this way, to support DPP in AE, we can benefit from DPP and AE at the same time. And another improvement on DPP is the equivalence inferring. We should know that DPP is also a kind of filter expression. And so it should be applied. So it's okay to apply the DPP for filtering, inferring, and push down. The logic should be similar, but one thing which is different is that there's equivalent class. If there's equivalent class for join condition, for example, if we have a join condition which is from table A and B, and we also have a DPP on table A. So we should infer that the DPP subquery filtering can also be applied on table B. So, but the logic is different from the simple expressions filter, infer, and push down, because we need to change the pruning key in the DPP subquery from table A to table B. So this is the way. But there are some tricky cases because, for example, we have a join structure like this. We generate a DPP subquery from A and then push down to the subtree, but we can only push down to table B. For table A, we even there is an equivalence class join condition, we cannot push down because this is the same table. So we add some logic to avoid users DPP inferred and applied. And runtime filter is another optimization that we implemented in eBay's Spark SQL engine. Runtime filter's semantic is similar with the DPP, but it's not on the partition column, it's on non-partition column. Since it's on non-partition column, so it's high cardinality, and we cannot filter just the table partitions directly. So we import the range and the Bloom filter. For example, we calculate there is a small table which can be broadcasted, and we calculated its min-max and the Bloom filter of the join columns, and then we push down it to the big table at the left and filter the big table Paquet trunks with range and the Bloom filter. This is how we do with runtime filter, and but currently we only implement the logic for broadcast join because it's easier to be implemented. And another tricky thing in runtime filter is that if there's many join conditions, how to apply the runtime filter. So let's talk about when to infer in the runtime filter. We have some checks and the limitations to avoid the bad performance. So firstly, if there's already a runtime filter on one side, we don't need to infer. If both sides can be broadcasted, there's no need to infer. And we also check the join type. For example, inner left semi right outer can prune the left, and inner left outer can prune the right. We also have some limitation configurations. For example, by default, only single table can be runtime filter build side. If allow multiple tables, build side cannot have subqueries to avoid too many nasty subqueries. If we allow the build side to have subquery, build side leaves should not have intersection with other side leaves in case of loop dependency. If there's an existing single column and equal to filter on pruned side plan, no need to apply runtime filter for this column. If the column data type is not orderable, no need to apply runtime range filter for this column. If the column data type is not supported in Bloom filter, no need to apply runtime Bloom filter for this column. So the next question is how to support multiple columns. Because if we apply the runtime filter column by column, we will have many subqueries, and which will make the performance even worse. And to support the multiple columns, we put the min-max and the Bloom filter into a struct type because Spark supports ordering of struct type. If only the types in the struct can all be comparable. So we put all the multiple columns into a generic internal row and compile the struct as a whole when we do the evaluation. One tricky thing to notice is when we push down the struct type, we need to split it into expressions of single column. For example, if we have 3 columns, we put it into abstract firstly, and when we push down, we will generate 6 filters for the 3 columns, which is greater than or equal to, less than or equal to. And the next topic is about how to plan the runtime filter subquery. We define 2 more physical nodes, which is in range subquery exec and in bloom filter subquery exec. So in the in-range subquery node, we calculate the min-max for broadcast hash relation, generate the codegen code for min-max comparing expression, and also we do the similar thing in bloom filter subquery. We calculate the bloom filter from the broadcast hash relation, generate the code for in bloom filter expression. We know that we have both DPP and the runtime filter in our engine optimization, so we need to avoid the conflicts between the 2 optimization. For example, we should not infer runtime filter with partition keys, and if we have a DPP on table 1 from table 2, we should not infer runtime filter from table 1 to table 2 to avoid loop. We should also have exchange reuse logic for runtime filter subquery. The exchange reuse logic is separated into with AE and without AE. Without AE, we just extend the reuse exchange rule to handle the in-range subquery and in-bloom filter subquery logic. And with AE, the implementation is similar with AE plus DPP. Firstly, we generate the subquery map in insert adaptive Spark plan rule, and then we reuse stage in AE logic. And then when we need to fall back the subquery filter to, when we need to fall back the stage reuse, we fallback the subquery filter expression to true, which is implemented in the adaptive subquery exec. Here's our performance results. We've done the runtime filter performance test on the TPC-DS 5 terabytes dataset, and you can see we have big performance increase in some of the queries, for example, like the Q72. Yeah, that's all of my content. Thank you for listening, and looking forward to the questions and communications. Thank you.